This chart shows Python's massive footprint in the 2026 tech landscape. It currently holds a 68% market share in data science and is utilized in 85% of all published deep learning papers. But this dominance presents a glaring technical contradiction. Python is an interpreted language, meaning it translates code line by line at runtime, rather than compiling it into machine instructions in advance. Because of this heavy runtime overhead, it is notoriously slow compared to compiled languages like C++, Rust, or Java. Professional developers are acutely aware of this drag. Scroll through any programming forum and you will easily find developers complaining that native Python code is, quote, as slow as a sloth. How does a language with such severe performance limitations become the undisputed backbone of the high-performance AI boom? The answer reveals a strict rule of modern software economics. Optimizing for human time and developer ergonomics yields higher returns than optimizing for raw machine time. In 1989, at the CWI Institute in the Netherlands, the original goal for Python was to bridge low-level system complexity and high-level ease of use. Creator Guido van Rossum wanted to make programming highly approachable for beginners. He even named the project after his favorite British comedy troupe, Monty Python, to ensure the language didn't take itself too seriously. This comparison illustrates the Zen of Python. By adhering to rules like beautiful is better than ugly, Python forces a sparse aesthetic. The community fiercely protects this, even protesting the walrus operator until Van Rossum resigned in 2018. Python intentionally sacrificed raw machine speed to enforce this visual clarity. By stripping away unnecessary brackets and boilerplate text, it drastically reduces the hours developers spend reading and debugging code. To compensate for its slow internal execution, Python operates primarily as a glue language, a lightweight interface used to coordinate entirely separate, faster systems. Instead of heavy computational lifting, developers write simple routing logic in Python, handing off intensive processing to optimized C++ libraries. This relationship powers modern machine learning. In TensorFlow and PyTorch, Python routes data processed by C++ under the hood. This minimal syntax also scales efficiently across web development. It allows teams to build massive, fully featured platforms using the mature Django framework, or spin up lightweight, async-friendly microservices using FastAPI. By offloading raw processing power to its surrounding ecosystem, Python achieved massive scalability without forcing data scientists or web developers to learn low-level memory management. As Python transitioned from simple scripts to massive enterprise backends, its dynamic typing, where variables can change their data type on the fly without warning, became a critical liability, causing codebases to tangle and break. To stabilize these large projects, an update known as PEP 484 introduced an optional feature called type hints, bridging the gap between dynamic flexibility and static safety. By explicitly labeling data types, developers enabled automated static analysis tools to catch errors and safely refactor code before it ever runs, all while preserving Python's native readability. With type safety addressed, the most notorious bottleneck remaining in Python's architecture was the global interpreter lock, or GIL. The GIL acted as a strict traffic cop. While it successfully prevented memory race conditions by ensuring only one thread of execution could run at a time, it completely restricted Python from utilizing true multi-threaded processing on modern multi-core hardware. That structural limitation is finally breaking down. Through PEP 703, the GIL is now an optional build configuration, allowing Python code to execute in parallel across every available CPU core. Making this move required CPython's entire memory model and reference counting system to be redesigned. The engine now uses localized atomic counters to maintain safety across multiple active threats without a global bottleneck. Altering the language's foundation required a phased rollout, an experimental opt-in in Python 3.13, before becoming an officially supported build in version 3.14. After decades of relying almost entirely on external libraries for speed, Python is upgrading its core architecture to handle modern, high-concurrency workloads natively. Are you Team Django or Team FastAPI? And do you plan to adopt the new GIL-less Python in your next project? Let us know down in the comments.